you. A very good morning in India and good evening in the United States to all the esteemed panelists and the audience present today on the occasion of Science Day Lecture 2021, organized by Indian National Academy of Engineering. I now hand you over to the proceedings of the day to the chair, Professor Indranil Manna, President, Indian National Academy of Engineering. Professor Indranil Manna, sir.
Thank you, Oral Rai. This is a very happy occasion. And the most important thing is that it is for the first time we are very privileged to have a Nobel laureate in physics delivering the National Science Day lecture organized by Indian National Academy of Engineering. Sir Chandrasekhara Venkata Raman was born on 7th November 1988. We all know he was awarded the Nobel Prize for Physics in 1930. He was not only the first Indian, but also the first Asian to receive Nobel Prize in Science from Asia. As a child, Professor Raman was quite a prodigy. He finished his school level class 10th examination when he was 11 years old and completed higher secondary when he was only 13 years old. Finished BSc in another 3 years and then went on to take his Master in Arts. At the age of 19, he joined Indian Finance Services as the Assistant Accountant General. In fact, he was posted in Calcutta, and when he joined Indian Association for the Cultivation of Science, which was the foremost scientific organization in India, founded in 1876. At that point of time, Raman was actually employed in the Accountant General's office, and science was not his profession but passion. And this is something which cannot be missed, that a person who actually had a full-time job in the Accountant General's office and used to pursue science in the evenings and his leisure time became so passionate and so effective that eventually he went on to discover the so-called modified effect in his own words, but actually Raman effect, which is all about change in wavelength and amplitude of waves scattered in a particular medium. Raman was offered Palit Professorship by Dr. Ashutosh Mukherjee. In fact, there was quite a bit of controversy at that point of time because he didn't have a PhD degree. Yet he was appointed the Palit Professor in 1917. And we all know that he pursued his full passion for science afterwards with his students, and most notably K.S. Krishnan, with whom he published the paper which fetched him the Nobel Prize. Raman was made the director, the first director, first native Indian director of the Indian Institute of Science, Bangalore, in 1933. The same year, Raman founded Indian Academy of Sciences in Bangalore and continued in Bangalore until his death. So he retired in 1948 at the age of 60 and founded another very famous institute, Raman Research Institute. He was awarded Bharat Ratna, the highest civilian award in India, in 1954. What is very important for all of us to note is that the National Science Day is observed in India not to celebrate Raman's birthday or any other occasion, but the most important fact that the Raman effect was discovered on this very day. So it is the spirit of science which Raman personified and epitomized. That is what we are celebrating today. We're extremely fortunate to have, as I said in the beginning, another Nobel laureate in physics, Professor David Weinland, to give the distinguished lecture today. And I would now request Dr. Debatosh Guha to kindly introduce today's distinguished speaker. But at the same time, I must also acknowledge the contribution of the Calcutta chapter of Indian National Academy of Engineering to have organized this particular lecture for us. So over to you, Debatosh.
Thank you, President. I'm honored. Dear fellows and friends, it's a great honor and privilege to introduce our today's speaker, Nobel laureate Professor David Jeffrey Weinland. The slide bears a little bit, but I'm trying to make a little bit elaborate, but I won't take much time. Professor David Weinland is now with the Department of Physics, University of Oregon, as Philip Knight Distinguished Research Chair. Professor Weinland is a recipient of 2012 Nobel Prize for Physics for his groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. Professor Weinland and his team kept ions inside a trap by surrounding them with electrical fields and manipulated their states with laser light at their laboratory at National Institute of Standards and Technology, Boulder, Colorado. His group was the first to demonstrate a quantum logic gate operation with two isolated quantum bits. Their ion clocks are use ultraviolet light, and hence their name optical clocks. It is just now mentioned by your president about Raman's contribution and Raman's work, and that's why it is too relevant to our Indian National Science Day. The discovery of light scattering through a transparent material took place in the city of Kolkata, where right now most of us are sitting. And it happened on this very day, 28th February 1928. For the same discovery, Sir C.V. Raman was awarded Nobel Prize, as already mentioned, for physics in 1930. So it's our homage to this great son of India on this occasion by another Nobel laureate, Professor David Weinland. David Jeffrey Weinland was born in Milwaukee, Wisconsin in February 1944. The family moved to California, where he gained his BA and at University of California, Berkeley in 1965. He earned his PhD at Harvard under Professor Norman Foster Ramsey Jr., who received the 1989 Nobel Prize in Physics. Weinland then worked on electron traps with another Nobel laureate, Professor Hans Demlet. It was at the University of Washington. In 1975, he joined this National Bureau of Standards, where he started his own group. He is also on the physics faculty at the University of Colorado. In January 2018, Weinland joined the University of Oregon as a Knight Research Professor. We are honored today to have this eminent personality in physics on the occasion of our Indian National Science Day. So may I invite with this word Professor David Weinland.
Yes, thank you for the nice introduction, and I'm pleased to be able to speak to you today. So I'm going to talk about two things which maybe at first don't seem like they have much in common, but basically we use the same systems for both of these things. So I'm going to talk a little bit about how we use single atoms. In our case, it's going to be atomic ions, but certainly many groups are doing similar experiments with neutral atoms. Anyway, we use the atomic ions in our experiments, and so that I'll explain a little bit how we can make clocks out of these atoms, but also I'll talk a little bit how they can make bits to store information. And the idea there is that typically we take two energy levels here, just labeled 0 and 1 on the bottom of the screen. So anyway, I'm going to, as I said, I'm going to talk about how the atoms can be used both as clocks and also as bits to store information. So first talk a little bit about atomic clocks. And first, I'll say, why do we want precise clocks? And I'll say a little bit about atomic clock basics and what people have been doing, including the lab at NIST, has been looking towards optical or atomic clocks based on optical transitions. And really the reason for that is just that with much higher oscillation frequencies, you can divide any interval of time, say the second, into smaller and smaller intervals because of the short period of the oscillation. And I'll say a little bit then about what the status of things are and where the future might go. So why precise clocks? And for centuries, one of the main applications has been in navigation. And I think if there's any sailors out there, they know how the traditional method works, and that is that the sailor on the ocean can say if he wants to find latitude, you can, in the Northern Hemisphere, for example, look at the North Star, and then the direction between his line of sight for the star and the local level is a certain angle, and that angle is unique to what his position of latitude. Now, the idea, of course, for longitude, it works the same way, except that since the Earth is rotating, you have to know what time it is to know how that fits into this relative angle to be able to determine your position in terms of longitude. But of course, these days the modern way to navigate is via satellites, and a well-known system is the so-called global positioning system. And the key thing here is that the idea is that idealized is that you have a system of clocks, and you on the Earth have one a high-performance clock. And the idea is that in the simplest form, it's exactly synchronized with a clock on board the satellite. So the idea is the way that you find the distance between the satellite and you on the Earth is basically, you agree on some pulse protocol, and it's more complicated but for simplicity, suppose you agree that on every second tick, the satellite emits a pulse, and then there'll be a delay because of the finite speed of light, and the length is then just given by the speed of light times the delay time from when the pulse was emitted to when it was received. And just to give you an idea of the errors these days, if the clocks are synchronized to a nanosecond, that gives an imprecision of this length of about 30 centimeters. And this also, of course, the clocks are continuously running. So this 1 nanosecond per day is about a part in 10 to the 14th. And that also gives the requirement on how regular the clock, the tick rate of the clock, the frequency of the clock has to be. So it's also about 10 to the minus 14 per day is what's required to get to this level of 30 centimeters. So the global positioning system, of course, is a network of satellites, and you can get, by having satellites, positioned at different places, then you can get all three dimensions. And also, the system is, I don't know the exact details of the system, but it's more than 4 satellites, and so there's a lot of checks between the satellites, and you can derive both your position and time by the synchronization processes that go on. So what about clocks? And the idea is about as simple as, I mean, physicists think about it, I think, pretty much the same way people that don't have a scientific background. And the idea is very simple to state. You have some periodic event generator and then a counter, and that allows you to generate units of time or the absolute time. And some traditional event generators are of course, the rotation of the Earth. And a very good clock was actually through the 20th century was the pendulum clocks, and they were about the best clocks in the early part of the 20th century. Now we have quartz crystals and so on, but the pendulum clocks are still very good if the system is made right. So, but these days we think about using atomic oscillations, and the atomic oscillations are very much like a pendulum clock. We have to think more in the lower left picture there. You have this kind of the classic picture of electrons orbiting a nucleus, and the orbits can provide this periodic oscillation. More precisely, we think about quantum mechanics, and there we have to think about wave functions. And the picture is not so much different, but for example, for these two levels, if we put them into a superposition, basically the frequency of oscillation of this superposition state is basically the frequency difference divided by Planck's constant, and that's what gives us the frequency that we use to generate the time. So I show on the picture there sort of the electron oscillating density versus time, and you can see that now that because of quantum mechanics, the wave function is smeared out a bit, but the basic idea is just the same as the classical orbiting electrons. And so one way clocks can be made is with a maser or laser, and of course everybody knows about lasers, and masers it's the same exact principle. M just stands for microwave, and L stands for light, of course. But the idea is that if the atom has an electric dipole transition, that dipole will emit radiation, and then basically all we need to do is count cycles of the emitted radiation. Now these days we do things a little differently. One of the problems with both the masers and the lasers is that because they involve a cavity that surrounds the atoms or atom. This forms a system of coupled oscillators, the cavity and the oscillating atom, and so if the frequency of the cavity is not tuned right, it can shift the frequency of the maser or laser, and that causes difficult problems to calibrate that out. So the way we think about and this is I got off track here. Sorry about that. Anyway, it was mentioned. I was a student with Professor Ramsey at Harvard, and Ramsey and his colleague Dan Kleppner had just recently demonstrated the hydrogen maser when I was there, and so this was Norman's group in 1967, pretty big group. And anyway, my project was to build one of the maser for one of the other isotopes, deuterium. So that was the main part of my project. So this is Norman standing there, and that's me trying to get close to the boss you see on the side. Anyway, so it was a really good group, and Norman was a really nice guy, terrific person to work for. So the more common mode of operation versus maser or laser is that we think about first initializing the atom or atoms in the lower state of the transition that's used for the clock, and then we apply radiation at a frequency near the fundamental frequency of the atomic oscillation, for a certain amount of time. Oops, my video didn't seem to, my animation isn't working. Anyway, you have to imagine radiation coming out of the radiation source there. And anyway, after we apply this for a certain amount of time, we measure the probability of the atom being promoted to the upper level of the clock transition. And the transition probability is maximum when the radiation source is equal to the fundamental frequency of oscillation given by the energy difference in Planck's constant. So when this condition is met, then we just, rather than counting the radiation coming off of the atom, we count the radiation coming from the source here. So why atomic clocks? And there's many reasons, to choose atomic clocks. I just, give a couple of examples here. I wrote down the simple expression for the pendulum clock oscillation frequency as a function of the acceleration of gravity and the length of the pendulum. And then we think for atoms, we think about storing them in some kind of box. And in fact, many of the early atomic clocks were based on microwave transitions, and this box was just a glass sill that had the inside coated with some kind of material. Teflon was one, where the atoms would bounce off the walls, not stick to the walls, and their frequency wouldn't be perturbed too much. So anyway, we have to worry about all kinds of effects. So one environmental effect we have to worry about is temperature. So for the pendulum clock, one thing we have to worry about is that if the temperature increases, and for most materials, the length of the pendulum will increase. And so for a one made of a very good, low expansion coefficient material, the frequency change per degree C, I'm not going to walk through the numbers, but you can just see it's about a part in 10 to the 8th per degree C. And it's negative here in this example because it just expresses the fact that as the temperature increases, the pendulum gets longer and the frequency slows down. So temperature also affects our atomic clocks based on the right there. And what the interesting thing here comes from Einstein, and what Einstein told us was that it's not like this pendulum clock where there's just mechanical effects that causes it to slow down with temperature. What Einstein taught us is that if the atoms are moving corresponding to a certain temperature, actually time slows down, and not just the oscillation of the atom. When we observe the oscillations of the atom, they run slower due to this time dilation effect that Einstein came up with. And just to give an idea, I'm being covered up by my picture here. Let me just see if I can get rid of these things. I got rid of me now, or that thing. Let's see. Yeah, I'll leave it on there. I can't get rid of this thing. So anyway, so I do a simple calculation there based on Einstein's expression. And so I come up with this temperature coefficient. So for cesium cesium 133, mass 133, this fractional frequency shift versus temperature is about a part in 10 to the 15th per degree C. So about 7 orders of magnitude smaller than the temperature coefficient for the pendulum clock. So that's one of the reasons we use atoms. And the other thing you can ask about is reproducibility. And of course, with a mechanical device, that the length of the pendulum clock here depends on the local manufacturing tolerances. Of course, it also depends on G and little g, and G is not the same on every point on the Earth, so that'll cause the frequency to be different. Also, we have, in the case of the mechanical, we have to worry about wear on this bearing that holds the pendulum, and that causes the length increase in frequency to go down. So for atoms, what's nice about atoms of a particular kind, say cesium-133, is as far as we know, they're exactly identical. And the other thing is they don't wear out. If we have a cesium clock and we keep those same atoms around forever, we can keep reusing them. Their characteristics just don't change as opposed to a mechanical clock. And since I've been talking about cesium, I think probably most of you know that the definition of the second is based on the cesium hyperfine transition. And the hyperfine transition is given by the fact that the energy levels that give rise to the oscillation frequency are just due to the difference of whether the electron's magnetic moment is aligned with the nuclear magnetic moment or anti-aligned. That's the energy difference. And this has been the definition of the second since 1967. And it still is the definition. And I think the clocks we have now, I'll try to explain it, they're a bit better, but it's amazing how good the definition was, because it's lasted for such a long time, since 1967. It's an amazing choice. So I'm going to talk about atomic ions in traps, and it was already mentioned. I worked for Hans Demel as a postdoc at the University of Washington, and this shows a schematic of one of the kinds of traps that we use for atoms. And the idea is that to this electrode structure, we apply a combination of static and oscillating electric potentials. And so it takes a little while to go through it, but any of the students out here, wouldn't have any trouble figuring this out. It just takes several lines of math to figure out what's going on. But the basic result is with these applied potentials, then at the center of the trap, we realize a three-dimensional harmonic well. And it's kind of a quick analogy to that, a 2D analogy to this is it's just like a marble in a hole. So why use, or let's consider atoms with optical transitions. And I mentioned earlier, one of the main reasons we think about optical transitions, it's just that the clock rate, the tick rate of the clock can be much higher, and therefore we can define the interval of time into finer and finer units. So I'm going to talk a little bit about this experiment on Mercury, which was the first experiment we tried to realize a clock on. And one thing that's kind of funny is that, I ran across this article. It was written by this fellow down here, a guy from NIST, and he found an old text that was actually from Lord Kelvin and his colleague Tate. And anyway, they wrote a text in 1879 which said that recent discoveries indicate natural, and I can't read it, it's so covered up, unfortunately, on my screen. But anyway, let me see if I can move this thing. Sorry about this. No.
Dave, maybe you can stop your video so we don't see your face. So that.
Well, wait. I was having trouble because my screen is covered up by my picture and then the speaker. The boxes for the speakers. I can limp along there, I think. So no. So is that okay for you now? Can you see me or no?
Yes, it is. It is clear now.
Okay. Anyway, this works a little better for me now. So anyway, we started thinking about Mercury in 1981, and the person that led this project from that time on was my long-term colleague Jim Berquist. And so I'm going to give you a little bit about that story, how this experiment progressed. So the transition we chose to look at was this electric quadrupole transition. It's in the ultraviolet at about 10 to the 15 hertz. And I give the atomic notation here, but we can, again, use the labels 1 and 2 for the ground and excited states. Anyway, what we want to do is we want to drive transitions between these two clock levels. So we're going to start the atom here, and then we want to be able to tell when we drive this transition. And so And of course, one of the features of of the optical transitions we choose is that they tend to be fairly narrow. So this particular one in Mercury has a lifetime of about 1/10 of a second. So this is the width over with the absorption curves. The absorption occurs is quite narrow, several hertz, and that gives us very good discrimination on where the clock laser is tuned. And so this is kind of traces out the Lorentzian line shape of this absorption feature. So how do we detect? So it turns out there's another transition in Mercury you can use, and it also involves the lowest energy state for the clock. But in this case, we drive up to another level which is electric dipole, and the lifetime of this level is extremely short compared to the lifetime of the clock level. It's about 2 nanoseconds. And the idea here is that when the atom, if the atom is in the ground state, then we can scatter a lot of light off of this transition here. I keep getting covered up. Anyway, so if we try to drive this, let me back up. If we try to drive this transition and say the clock laser is mistuned a little bit, then after we attempt to drive it, the atom will remain in this ground state. And then when we turn on this second laser, we'll see lots of scattering. On the other hand, if this clock laser is tuned to the resonance of this transition, then when we turn on this second laser, we don't scatter any photons. There's always some stray scattered light, but the difference is extreme. So when this transition is connected, we scatter about 20 million photons per second. And if we just collect a few of those, then we can easily tell whether the atom was in this lower state or the upper state of the clock transition. So in fact, we can even see a single atom. And of course, well, not quite, because this radiation we're using on this particular transition is in ultraviolet. So we can't see it with our eyes, but we can, we often use a ultraviolet sensitive video camera. And so we can make a picture of this. So you see an ion in the center of this electrode structure, and some of the scattered light off of the electrodes, the center electrode and the separator electrode. And actually, some ions that people use, barium, singly ionized barium is a interesting one, because its fluorescence for this strong transition is in the blue, and you can actually see it with your eye. And the other thing, maybe another interesting to say about this picture is this: in this picture of the ion, that the resolution is limited just by the optics we had, and actually we can show by other means that the wave function of the atom is about 500 times smaller than this dot that you see in the picture. So we can also, it turns out, we can use this transition that we're using for detection to also cool the ions down. And the reason this is important is we can suppress this time dilation shift of Einstein's. And the idea there, the simplest form of cooling is actually relatively easy to explain, and that is the idea. Of course, when the atom scatters light from this incoming laser beam, there's momentum. The momentum kicks from the photon scattering are imparted to the atom. And what we do is we for this particular form of cooling is we just turn the frequency of this laser slightly below where it wants to absorb this frequency, the radiation at maximum. And so because of the first order Doppler shift, then when the atom moves towards the laser beam, it scatters at a higher rate than when it's moving away from the laser beam. And so the overall is a net damping force. And just to give you an idea of the numbers for this so-called radiation pressure laser cooling, in these early experiments, the apparatus was at room temperature, about 300 Kelvin. And with this, through this laser, and the atoms or the ions would be at that temperature as well if we didn't do anything. So, but with this simple form of laser cooling, we could bring the atoms down from about 300 Kelvin to about 1 millikelvin. And this is important for the, for the, as I say, for the, this time dilation shift that Einstein told us about. So this is a picture just not long after we did those experiments. And these particular experiments I did with Bob Drollinger here on the right. And here's another picture of Jim. And this is Wayne Atano, who had joined the group a year or two earlier before this picture was taken. And he's sort of the theorist in the group and helped in a lot of ways on these experiments. So there's a lot of details in improving the clock space on these Mercury events. And I'm not going to go through all those details, but just a couple of the features that we're able to realize in these kind of experiments is, first of all, that the trapping, just the fact that they're trapping them, the ions are trapped, the average velocity goes to 0, and that means that the first order Doppler shift also goes to 0. So we get rid of that effect just from the trapping. And then the laser cooling reduces this time dilation shift. And as in the later experiments, we went to 4 Kelvin, and among other things, that gives us a high vacuum. So basically, all background gas, except for maybe helium, is frozen out on the walls of the electrodes. And and there's other shifting. So pretty much get rid of it. The other thing is actually we have to worry about the thermal radiation in the room, so-called black body radiation. And the nice thing about going to low temperature is that the shifts from the black body radiation goes as temperature to the 4th power. So by going from 300 Kelvin to 4 Kelvin, we don't totally get rid of it. We highly suppress the so-called black body shift. So the nice thing, Jim certainly had a feather in his cap at this experiment, because what was significant about this experiment, this Mercury experiment, was that in 2006 we could show that the systematic uncertainties, temperature, time dilation, et cetera, were lower than the total uncertainty for the cesium clock. So the uncertainty in 2006 was about 7 parts in 10 to 17, but that was better than the current the cesium clock, and that has remained the case from that time on. So I've said a little bit about many of the frequency shifts you have to work on. I haven't mentioned some of the more mundane ones, but common ones that we have to worry about, and that is that we always have stray electric and magnetic fields in these experiments. I talked a little bit about thermal radiation, but we have to, for example, for magnetic fields, that can shift the frequency of the clock transition. But what we do in the case of Mercury, and this is common in other clocks too, you measure other transitions in the atom or ion that are much more sensitive to magnetic field, and then you can calculate their effects on the clock transition. So some of the other interesting effects are, of course, Einstein again. I've talked a little about the time dilation shift due to motion. There's a second one he told us about. This came from his theory of general relativity, and what he showed was that that time runs slower in different gravitational potentials. So we call it a red shift because if our clock is in a stronger gravitational potential, it shifts the frequency of the transition down. And so this is, again, a very fundamental effect. It's not that somehow doing environmental perturbation on the atom, it's time that slows down. And just to give an idea, these effects are not small. I mean, we're down now measuring things that, certainly below the Barton 10 to the 15 level. And the redshift, this gravitational redshift from the Earth at sea level is about a Barton 10 to the 8. So this is an important thing that we have to think about when we're, comparing clocks, say the clocks on the Earth to the satellite clocks. So it's a big effect that we have to calibrate for. And just another thing to think about is if we compare two different atomic clocks, we have to know their relative heights because of this shift to the red shift. And so I'm not going to go through I wrote down an expression for what the shift is for changes in height, delta H there. And it's not a big effect. In fact, it's sort of interesting to think about how it affects us on a human everyday scale. So a little story here is that suppose you and a twin sibling were separated at birth, and you live at sea level, and your twin lives at Boulder, about 1.6 kilometers above sea level. After 80 years, your twin will only be about a millisecond older. So it's as I say, it's a small effect on a human scale, but it's an effect we can observe with our atomic clocks. So this was just a fun way of doing this. There's been more accurate measurements of this gravitational potential redshift, but this is an experiment we did in the lab. So this is a picture of our aluminum clock. We've switched to aluminum now for various reasons. One reason is I mentioned that we get higher resolutions with longer and longer upper state lifetimes, and this aluminum has a lifetime of about 20 seconds. So the absorption feature in the clock transition is much narrower, about 200 times more narrow than the aluminum, than the Mercury clock. And this project has been headed up by David Librand in Boulder, and he continues to do that. So I'm going to call this clock number 1 that you're seeing. Doesn't look much like a clock. I'm not going to try to point out everything, but what you can see in this picture is maybe this long silver tube actually holds the ion trap in there, and the rest is just optics. So anyway, for this little demonstration, you can see James Chow, who was one of the principal people on this experiment. As you can see, he's put jacks underneath the table here, and what he's going to do is raise this up. Oh, I should have first said sorry. I jumped ahead there. So we have a clock, not exactly identical, but as near identical as we can make it in an adjacent room, and its height above the floor is the same as the clock you see in this picture. And so what you can see in this picture, James is raising up this first clock at about 40 centimeters, and I keep forgetting my lines here. So when we measure the frequency of these two clocks when they're at the same height, and the two about apart in 10 to the 18th, the frequency ratio is 1. So after raising these, the one clock, it runs faster because it's in a weaker potential, and so the ratio of the frequency is about 40 parts in 10 to the 18th faster for the clock you see in the picture. So we can actually see these effects even though they're extremely small. So there's a lot of things I actually have to go through here, and but just isn't simply enough time. But just to give you a rough idea of kind of where we're at, the whole field, people working on these clocks. Most accurate clocks are based on optical transitions in ions and neutral ions. And the total uncertainty expressed factually is around a part can be 18 for the best clocks. So what about the future? Well, in fact, I mentioned the importance of navigation at the first, and that's still a very important application. And now that the best satellite systems are down roughly at a level of 1% or centimeter, maybe better. I mean, some of this stuff is certainly behind the door, but anyway. But one thing people have thought about, a useful practical application may be that, say, we can measure via the clocks or the like the satellites, or by the gravitational redshift. And, 1 centimeter corresponds to an uncertainty of about a part in 10 to the 18. And so one thing people thought about is actually maybe the clocks in different locations, by comparing it, could be used to measure earth strains, changes in the level of the heights of the relative heights of the clocks separated by many kilometers. And the reason this might be interesting is that certainly strain is a precursor to earthquakes, and so maybe by doing these kind of measurements, it would help in earthquake prediction. And of course, just as scientists, there's many fundamental things we like to test. I mean, certainly people with gravity wave detections, people have come up with schemes how we might do it with clocks and even search for dark matter. And the other thing that we've done over the last 10 or 15 years is to test for different clocks. The clock frequencies depend on different ratios of the fundamental forces like weak, strong, electromagnetic, and so on. And so by measuring two clocks based on different atomic species and looking for their long-term behavior, maybe we could put limits on whether or not the basic forces of nature are changing. And of course, it's always been a sport to try to prove Einstein wrong, but so far he's held up pretty well. We haven't found anything wrong with what he told us. Okay, I'm gonna switch gears now and talk a little bit about atoms as information bits. And so we're actually in these experiments, with some changes, the characteristics of the atoms we use for the clocks are very much as the one we use for atomic bits. And so the idea is that suppose that for a clock transition, suppose the upper state, oops, I changed the label on here. So suppose the upper state has a very long lifetime, then we can store information in the lower and upper state, and we can just label those energy levels now rather than 0, 1, or 1 and 2, we label them as 0 and 1 to store information. And we can actually do this. We can make a classical single bit memory this way. But it turns out if we drive this qubit now transition part way, we can make a superposition state, just very much like the oscillating electric dipole superposition that I showed before. But in this context of information, what's interesting is that this will expand in principle, extend our ability to do computations. And just to give you an idea of kind of how weird this is one of the toy experiments we can do in the lab. We can take a single ion, put it in our ion trap, like a marble in a bowl, and we can actually make the ion roll back and forth in this bowl. So at one instant of time, it'll be on the right side of the bowl. And next instant of a time, it will be oscillate over to the left side of the bowl. But it turns out with this idea of superposition, we can make superpositions where the atom at certain instants of time is actually both on the left side and the right side of the bowl at the same time. And this makes no sense in our ordinary day experience, but this is kind of the world we live in. So one reason this idea of superposition is potentially interesting for computation is the following. So suppose that if we compare to what classical bits, then we classical computer bit stores, binary bit stores a 0 or 1. But a quantum bit, which can be in this superposition state, we can actually, in some sense, we store 0 and 1 at the same time, much like the particle and the atom in the trap being on the left and right side of the bowl at the same time. So why this is interesting is how this quantum memory might scale. And so, for example, suppose we so just consider a 3-bit register. So for a classical register, it can store one 3-bit binary number, say 101. For a quantum register, it can store simultaneously, in this superposition sense, all the 2 to the 3 or 8 possibilities of these quantum states from 0, 0, 0 up to 1, 1, 1. So in this superposition sense, it stores 2 to the 3 or 8 numbers simultaneously. So where it gets really interesting is if we have 300 quantum bits, this can store 2 to the 300 numbers at once, or about 10 to the 90th, and that's more than all the elementary particles in the universe. And so this looks pretty interesting, right? That you can have this massive parallel memory storage. But the other thing is that in general, I think most of you are aware, of course, this is the quantum mechanical expression for the wave function. And typically in these experiments, these coefficients alpha are different for all these different states. So in some sense, we can, in addition to storing all these 2 to the n numbers simultaneously, when we do a bit flip, then basically all these 2 to the n coefficients change simultaneously if we just flip one bit. So, but when we go to measure, then we have to consider, let me just say what happens with 1 bit. So if we have just a single bit, when we do the measurement, the atom or ion will either collapse to the 0 state or the 1 state with the probability given by the magnitude of these coefficients squared. And the same thing happens with our multi-bit quantum register. For example, in the 8-particle, or pardon me, the 3-bit quantum state, when we measure the register, it's going to collapse into one of these 8 possible numbers. So that might sound like a strict, even though we can talk about this fantastic memory storage, when we actually measure it, all of these states will collapse down into just, or rather this massive superposition state will collapse down into just one of these states. But in fact, Peter Shor was the one that really kind of, the people had thought of some of the basic ideas of, how you could gain advantage with these ideas of quantum computing. But what really set things going was a mathematician, Peter Shor, who's now at MIT. He came up with an algorithm that said if you could build this quantum computer, you could efficiently factorize large numbers. And the reason that's interesting, I think probably most of you know, is that most of the encryption we use, for example, RSA, it derives its security from the inability to efficiently factorize large numbers. So if we had this factoring machine that Peter Shor came up with, then we obviously that compromised security, and certainly that's one of the reasons the government got interested in these things. So just to also maybe carry this comparison a little bit farther, I'm not going to try to, I don't have time to try to prove any of this, but what the theorists have shown us is that for what we might call universal processing in the classical computer, that may not be the most efficient way, but basically we could do universal processing, almost basically any classical code with 2 logic gates, and it could be different ones I'm choosing here, but it could be a bit flip and say it's a 2-bit AND gate. There's a similar thing you can say in the quantum world. We need something a bit more complicated than the bit flip. In fact, it's what we usually call a rotation. So if we start with the bit in the 0 state, we have to be able to make a superposition state like this. And one way you can think about this is if you think about the 2 states of a spin 1/2 particle on the block sphere, when we do a rotation of this spin 1/2 particle, the rotation coordinates is given exactly by these expressions here. So that's the easy part. The other one is we need some sort of non-trivial 2 qubit logic gate, and I just give one example here. It doesn't look so interesting here, but in fact it's what we call a phase gate. So basically the truth table is written for when we operate on pure states, and the only thing that happens is for when both bits of these 2 qubits is in the upper state, then the wave function picks up a minus sign. Anyway, that and the rotations allow us to do universal computation, and including principle we're doing Shor's algorithm. And I'm not going to be able to explain Shor's algorithm. People devote semester classes on this and related things, but one thing is maybe interesting to think about is that so we started out with some big quantum register, and then in this case we could, in Shor's algorithm, we make an equal superposition of all the possible states, and then we basically operate this input state on these different logic gates, a combination of the rotations, and also this could be this phase gate that I described. And then one thing that's interesting about this, you can just think about what's happening in Peter Shor's algorithm and others. It's very much like this simple version here, this two-slit interferometer using water waves. And I think, we've almost all of us seen this in some early science class. But the basic idea is that the wave coming into this barrier that has these small holes transmits partly, but these waves can interfere either constructively or destructively. And Shor's algorithm is very much like this. The idea is that these in a very complicated way, these operations we do on the quantum register interferes all these amplitudes into that gives us a final state, which is something interesting. And this is what Peter Shor came up with the algorithm for what that interesting state could be. And it's a bit more complicated than what I'll say, but basically there's a certain probability of it collapse to a smaller number of states, but though any of those can be used in a classical number theory algorithm to determine the factors of the number you're trying to factor. And just to set the scale, the factorize 150-digit decimal number takes about 10 to the 9 of these operations, and certainly we're not anywhere near that now. The errors come into a lot of these experiments after a few hundred operations. Pardon me. So anyway, as far as experiments go, we're indebted to two of our atomic theorists, quantum optics friends, Ignatius Serac and Peter Zoller, and they came up with the following scheme, which I'll sketch out for. So this is another ion trap. Doesn't look like the one I showed you first. What we choose this kind of so-called linear trap is that basically it'll put the atoms into the string you see here. And the reason that's interesting is that we can then focus laser beams on the individual atoms. So each one of these has it's just like the single qubit I talked about. I'm changing labels here a little bit from 0 or 1 because I want to use the 0-1 notation for these motion levels. The other thing to think about is that when we have this in this case, this 5 ions in this trap, there's an overall harmonic well that holds the ions in place here. And we can think about the different modes. There's 3N modes, 15 modes of this kind of pseudo molecule that we've made. And basically we can spectrally isolate one of those modes. And then we can think about the quantum levels associated with that mode of vibration. And this is kind of the key idea for their scheme, is that Serac and Zoller's scheme is that they would use one of these modes. And the overall idea, and I'll say it works in a little more detail in a minute. So first of all, the first step in their operation is to start the motion in the ground state. So that was when the motion was in just that level. And then we can have a way to map the internal state superposition of this selected qubit onto to emotional state superposition, which replicates the superposition that was in the atom. And then if we can somehow figure a way to make a logic gate between this particular qubit and the motional qubits, which now reflect what was in this first qubit, then basically we made a logic gate between the first and second qubits. And in the end, we undo this mapping to get the to do our next step in the algorithm. So the way we do this with radiation, and I'll talk about, it's similar to talk about optical beams, although we do it a little differently with, in experiments. But basically, for us, if we have an optical qubit, this first mapping step that I showed there is simply given. We start out the atom. In general, this atom will be in a superposition of the spin down and spin up states, changing that notation. And then what we do is we drive a transition which drives this amplitude in this state down to this level here. And so now the superposition that was in our atomic state is now held as a superposition between this 0 and 1 motional state. And the way we do the logic gate is that, first of all, after we do this mapping step is basically this motion is shared amongst all the ions. The simplest mode to think about is the so-called center mass, where the ions are moving back and forth. Their spacing doesn't change, but they move back and forth in the horizontal direction in this picture, in the external realm. So we think about that when we use there's other bits that are a little better to use. But anyway, that's the basic idea. And the key thing about that is that then this motion superposition is shared amongst all those ions. So then when we go to try to make a logic gate between the motion and the second qubit, in general, before applying the operation, all these four amplitudes are occupied because of the first mapping step. And in fact, what we can do is we can drive a transition where the atom in this very upper state goes through down to what we call auxiliary state in the lower motional state, and then brings it back up. And just very much like when a spin 1/2 particle is rotated by 2 pi, you pick up a minus sign is picked up in this operation. And basically, this is then just the truth table for that phase gate that I showed you before. And in the final step, we need to do this, reverse the mapping operation, and then we've done this phase qubit, this phase gate between the two ions. So we did one thing that was nice to, actually a little bit of a backstory is Peter Shor and Ignacio Serac were at a meeting, the so-called ICAP meeting, International Conference on Atomic Physics, which I helped organize in 1994. They were at the meeting, and Shor's algorithm had just hit the airwaves, and so we actually brought Arthur Eckert, who's a theorist in this business, to come and give us a talk. And anyway, he told us about Shor's algorithm, and Ignacio Serac and Peter Soller were in the audience, and one of their strengths is, besides being very good theorists technically, is that they know how the experiments work. So they immediately picked up on this idea. They knew how the ion traps experiment, and they came up with a scheme that I've just described for how you would do logic. So what about scaling to larger numbers of ions? And so one thing, there's various ways to do this. First of all, it turns out, I mentioned that we need to separate out a particular motional mode to do these logic gates. If we put too many ions in one trapping zone, then there's just too many modes to spectrally resolve the different motional modes. So what we typically think about is making smaller groups of ions, and one way we could share the ions to share the information around is actually move ions between the different trapping zones. And in this picture here, so I say this could be a qubit that comes from this location here. We move it in here to do the logic gate between that ion and one of the other ions in this string. So that's one of the pictures, one of the schemes we think about. There's also ways to actually entangle ions in different zones optically. I won't go into that scheme, but that's certainly another scheme that people are working on. One of the other things, just one of the little details we have to worry about is that these operations are going to be over extended times. And one thing we have to worry about is all these, certainly the ion experiments, suffer from noisy electric fields, which will cause the these motional modes to heat up, and therefore compromise, their fidelity. So we typically think about having, another ion, could be another species of ion that we can apply laser cooling to. And for another species, the wavelength we need to do is going to be typically different than the wavelengths we use to make the logic gate between our logic ions, which are shown in pink here. And this just shows a picture. This was one of our early versions made probably more than 10 years ago by Jason Amini, who was a postdoc in our group. And this shows what we're taking advantage of here. It doesn't look like the trap that I showed, but basically this is all the electrodes in the surface, and the ions are held above this surface. And all these electrodes coming in make this grid of locations, zones. And for example, each one of these very small rectangles represents one of the zones we could hold ion into. And we call this a racetrack for obvious reasons, but the idea is this is a way to scale up the number of zones and therefore the number of qubits we can eventually operate in. And there's many groups working on this, and I can only list, I'm sure I'm not even up to date on this list, but this gives you an idea. These are just groups working on atomic ions to do quantum information. But there's many other platforms, as many of you know. There's certainly neutral atoms, which I mentioned, and then Josephson junctions, superconducting qubits, quantum dots, nitrogen vacancy. So anyway, there's many things, and there's also many companies now joining in the business. And actually, that website I list there is one which lists a lot of these companies that are getting into the game. Excuse me. So anyway, I showed the picture of our small initial group of about 4 people. We grew over the years, and this was the group the year I left this to come to Oregon. And of course, the groups of people you see here, the students, the postdocs, and visitors were the one that really did all the work in the lab. And so it was a huge effort from many people that brought about these experiments. And actually also, although the NIST supports these experiments, in fact, we really are helped by getting outside funding with these projects. And so these are some of the US agencies that help support these experiments. And also I should say that at NIST, I think we had great leaders, and I showed 2 here. So Catherine Gebbie was, very well-known Will-Light director for about 15 years, and certainly during the time that I was there doing the experiments I was involved with. And now that her position is assumed by Carl Williams, who's also doing a great job in keeping quantum very much alive at NIST. A little bit about how I got to where I'm at, and so just a little bit of a personal story. My parents lived through the Great Depression in the U.S., and so that was the depression from about 10 years around, from 1930 to roughly 1940. And they were lucky because they both had jobs that they held all the way through the depression, so they didn't have to worry. They had to be careful, but they didn't have to worry so much about financially. But they could see what the danger of not having a college education, was. And so they certainly, one thing they kind of drilled into me was emphasis on college education to find a good job. And so basically, the only rule for me was to maintain good grades in school, and that was, I liked school, so that wasn't a big deal. And the other thing, my father, he certainly encouraged me with just like simple math games. When I was very little, it was just say multiplying and adding numbers in rapid succession. And I liked it because my sister is a bit older than me. It's the one thing I could beat her at. So the other thing is that my parents, as long as I did well in school, they were very supportive things I did. So just to give you an idea, I mean, I was always interested in mechanical things, and you know, I started playing with model airplanes at age 11. I still do it when I can find the time. But also, when I got closer to high school age, my buddies and I, we were all interested in cars and motorcycles, that sort of thing. So I actually got my first car when I was at age 14, and I couldn't drive it yet. You couldn't get a driver's license in California, where I grew up, until you were 16. But my dad, I bought the car, and my dad brought it home. And so for the next year and a half or so, I tore it all down and built it up. But you know, and it taught me a lot about mechanics to do that kind of thing. And actually, you know, this went all the way through high school. So this picture is a group I was working on one of my friend's cars, and you might say, well, this is kind of just a lot of goofing around. But for me, one thing I can say is this is very much like working in a physics lab. There certainly was teamwork involved in working on these cars, and certainly in experimental physics, and certainly in atomic physics. Experiments are particularly involve lasers that are typically complicated enough that it's much more efficient to work in a team. So this experience of working with these guys on cars is, as I say, very close to working in a lab. And just a little bit about, I think in the introduction, I went a little about where my schooling. After high school, I went to the University of California, and I actually spent my first 2 years they were both, my undergraduate was at University of California, but my first years were at the Davis campus, which was close to where I grew up. And it had been primarily an agricultural school. And at that time, it was still very strong in agriculture, but not so strong in science. And Berkeley was only 80 miles away, so it was easy. It was easy for me to transfer there. It just took, all it required was a piece of paper. And so I finished my last 2 years at Berkeley, mainly and it was much stronger in physics. And then I went to graduate school at Harvard University from 1965 to 70. I told you a little bit about that work. And then I took a postdoc position with Hans Stamos. He was one of the inventors of the ion trap. And actually, Norman Ramsey, my advisor at Harvard, and my advisor at Washington, Hans Stamos, with Wolfgang Paul, they shared the 1989 prize for Ramsey for the Ramsey method of spectroscopy and his work on molecular beams and the hydrogen laser, and for Damalt and Powell, their work on the ion traps. So for that, I think I conclude here, and thanks for listening, and for all the students out there, I certainly wish you good luck with your studies and the rest of your career. So thank you.
So much, Professor Weinland. So no word is sufficient to express our feeling right now. Covered C to C, clock to computer, and vast experience of working with in different fields and different groups of people. And finally, your own very encouraging life story. Indeed, we are very much enlightened, and we have few questions from the audience. So with your permission, can I take a few?
Oh, certainly.
So I just mentioned one thing more, that in the panel, Dr. Amitabh Sengupta is present. So Dr. Sengupta is our primary connection through which we have brought you. And Professor Dr. Sengupta was professionally connected for last few years, I know. So I would also request Dr. Sengupta, so from your personal experience, if you say something, and about, you have some questions too to Professor Weinland.
Yeah, thank you very much, Debatosh. Well, I just have a short comment. Thank you very much, Dave, for accepting our request to give this wonderful talk. It's been really a fantastic exposure to the latest state of the art in atomic clock technology and also quantum computing. If, with your permission, may I ask a couple of questions? I'm just curious, in the 1980s, we were talking about clock accuracies, atomic clock accuracies at the level of 10 to the minus 14 or so. And today, 4 decades later, we are down to minus 18. So what's your outlook into the future? Will this still, how far will this go at this rate of 1 order of magnitude per decade? Will this continue further?
Well, I don't know, it's dangerous to make any predictions about that, but I think that one way to answer it is, and as I'm sure you know, and there's really no fundamental limit. It's, we can continue to improve the accuracy by just understanding the various perturbations in the system, and that's certainly the reason for the progress. So, ever since the mid '60s when atomic clocks were first made, the first cesium clocks, and so it's just a matter of getting better and better control on the system. One thing to be that I should point out is that one of the limitations we have, particularly with our single ion clocks, is that it takes a lot of averaging to be able to determine the center of these lines. So one of the advantages the neutral atom experiments have is that they deal with quite a bit more atoms than we do with our ions, several thousand. And so basically the signal to noise just averages down with the square root of the number of atoms. And so it's much better to have a larger number of atoms. And so, certainly the ion experiments are now trying to figure out how to build up to a larger number of ions for the clocks.
Dave, another little bit of curiosity. At one point in one of your slides, you mentioned when you were describing the possible uses of such fantastic accuracies in clocks, you were saying accurate clocks would be used to detect dark matter. I'm not familiar with dark matter and cosmology. Well, but just
I'm certainly not the expert, but the basic idea is that the dark matter, whether it's axions or some other field, basically when they pass by or through the atoms, they can perturb, they couple to the constituents differently, so they can shift the frequency. And that's the basic idea. That I personally don't know. I haven't looked hard at any of these these theories, which are admittedly largely speculative, but that's the basic idea, is that these fields, dark matter, can perturb the frequency. And so it's very much like the gravity waves could move the clocks, cause Doppler shifts that could be measured, et cetera, et cetera. But so anyway, I only have these classical notions, but it's those ideas that these fields that comprise dark matter or other periodic systems.
There are people working on this experiment.
Oh yeah. I mean, well, there's been quite a few theory papers, and if I could, if you'd like, I should send you a nice review paper that came out about a year ago.
Just for fun. Yeah, sure.
Yeah, sure.
Okay, great. Thank you very much once again for this wonderful talk. Thank you, Debatosh.
Thank you, Dr. Sengupta.
Right. So, can I read the questions, sir, for the benefit of the audience?
Yeah, sure.
Yes.
Thank you, sir. So the question is: can we use, or is there a possibility that the nuclear energy transitions between different, that is, nuclear isomers, rather than the atomic electron transitions, to increase our accuracy even further?
Yes, there's certainly several groups working on that. I think that obviously the person that asked the question has read about some of these things. And that, yeah, the idea there very briefly is that, it's fairly rare, but for example, in thorium 229, I think it is, there's a nuclear transition, which is between two for nuclear levels, nearly degenerate. And it's actually at an optical wavelength. It's not a real easy line optical frequency. It's about 150 nanometers. But anyway, but the ideas would be very similar to what I talked about. And one of the main reasons people think this might be interesting, other than just the novelty of being able to make a clock out of a nuclear transition, is that the nuclear, the nucleons are shielded by the outer electron cloud, and this shielding provides, great immunity from a lot of environmental effects that we see. So that's certainly one of the selling points. And yes, anyway, so people are working on it. There's groups including at NIST that are trying to get going. There's certainly, as I mentioned, one of the problems is the wavelength you need 150 nanometers. So people have demonstrated you can get very narrow line widths by doing harmonic multiplication in gases of lower frequency lasers, and get very high resolutions. But it's not like going down to your favorite laser store and buying one. It takes a lot. It's going to take a lot of work to do that. But certainly very promising, and it'll be really interesting to see how that goes.
Thank you. So it is just one common query or common interest, since we can directly approach you, see you right now, and on behalf of the audience, just one small question, that your work, so far our understanding, it is based on huge experiments. Am I right?
Well, there's experiments like at CERN. Now those are huge experiments. But I think the thing to say is that
well, it is extensive experiment. Can I say like that?
Well, I think the thing is that basically, for example, I described some of the very first experiments where we were doing laser cooling, and that was one, that was an important step, and it was one low power laser and a not very good trap. And in fact, I mentioned my colleague Bob Derlinger and I. We started with an empty lab, and 5 months later we had our first results. So it wasn't that complicated. And certainly, with all the other things we wanted to do, it got more and more complicated over the years. But so, I think that's more the typical route. They start out simple and then they.
So your passion, your experiments, that brought the prize finally, Nobel Prize. But the students, engineers, they're present in the audience, they may be interested to know that what kind of encouragement, frustration, pain, patience, all are related with these experiments and works.
I think all experiments certainly have, in addition to the rewards, there's a lot of dead ends, a lot of frustration, and a lot of mistakes made, and that sort of thing. So I think, though, a couple of things I might say to the students is that I think, the main thing is you have to do something you like. I think, on one extreme, if you go into a field to win awards, that'll be a disaster. You're not going to get very far unless you really enjoy the work and are willing to spend the time. And it will take, it'll take a lot. There's no question. It takes a lot of hard work. But I always said, and I do feel that the work is more like a hobby than a job. And I think, and so and it's very interesting too. So I think I think the real reward for all of us doing these kinds of things is that it's just the kind of interesting things we can learn and get out of these things rather than, the awards that come along. The awards are very nice, of course, but that's not the main reward.
So my last question. So if you have any message for the new generation researchers, students in science and engineering?
Well, I'll be repeating myself here a little bit, but I think it's really important to find something you're interested in, and because that way the work won't be so hard. And I would say even with the people that change, and one of my close students when I was in graduate school, he was a concert pianist. He'd gone to Juilliard, a very famous music school for several years, and then he decided he wanted to do physics, and so he'd made this huge switch, and yeah, he was very successful.
So passion is very important. So can I now hand it over to our president, sir, Professor Manna?
Yeah, Debatosh, but then there's one more question with permission from Professor Weinland. I certainly would like to read out this question because, this 100+ audience who have stayed tuned throughout your lecture on a Sunday morning, I feel obliged to actually relay this question coming from Prasad Power. And he says, to find, say, 2⁻n solutions to some systems of equation, a classical computer has to compute 2⁻n times. But a quantum computer using n bits can measure 2⁻n simultaneously. And we have to measure these 2⁻n times because of the collapse of wave function. So do we need 2⁻n different individual quantum systems to measure this? How is measuring for these individual states better than just computing 2⁻n times on classical computer? So his main question is that, yeah.
I can't give a comprehensive example here, but I think that, and I'm certainly not the expert, but I think what the theorists will often say is that the power of a quantum computer comes from entanglement. And that gives this exponential increase in efficiency in computations. And you can't get that just entanglement doesn't exist in a classical machine. So that's one answer. And a top theorist could give a much more detailed answer than I can, but I know that's certainly one of the issues is the entanglement that gives the power of the quantum computer. It's not, and people often talk about speed. The real issue is efficiency. It's just much more efficient than a classical computer. So, but I think you'd have to. That question should go to my colleague Peter Shore, the guy who invented the evaporator. People like him could give a much better answer than I can, I think.
Right. I think, quantum computing is related, but not necessarily exactly what you were talking about. So that's excellent. I have a very naive question from my own side. Does temperature play a role? I mean, we know frequency is not, but certainly the amplitude varies with time for any of individual species. So
you're talking about temperature now?
Do you need to maintain temperature for the device? Either it's a clock or a trapped ion, or the temperature, does it play a role?
Yeah, it may be indirectly. I mean, I've described the fundamental effect like the time dilation shift due to motion, and that's sort of at the fundamental level. And I would say that temperature is always important because things will drift as temperature drifts. A good example is in these experiments with lasers. The lasers are based unlocking to a cavity. And, they have to be extremely stable to probe these very narrow line widths. And so one thing we have to worry about there is just the temperature changes in the cavity can cause the cavities to change length and therefore shift the frequency. So that's one way temperature gets into these experiments. And, there's other things I could list too, but that's one of the important things.
Well, okay, so I think now I have to do the pleasant duty of thanking you, Professor Weinland, but I don't want to sound it very perfunctory. Honestly, it was not only a wonderful lecture, it was really fascinating to see how much of contributions and complementary contributions are required to arrive at an extraordinarily new conclusion, interface between both fundamental science and engineering. And we belong to Academy of Engineering, so obviously we tend to glorify the contribution of engineering even to fundamental science. And in our defense, we always quote certain examples like Einstein predicted laser in 1917, and we had to wait until 1960 till the time Myman actually showed the existence of laser. Similarly, it took us 100 years from 1916 when Einstein again predicted the gravitational wave, and we had to wait until 2016, exactly 100 years, till the LIGO actually proved the existence of gravitational wave. And there are many, many examples. I belong to the field of materials, like the prediction of dislocations and Guinea-Preston zones were all known, but proven with evidences not until the electron microscope came into being in the 50s. So, so what you actually presented before us certainly confirms our belief that just like the overlapping bands in metallic systems, there's no clear, sharp interface between science and engineering. They are overlapping and they contribute to each other. So in simple words, we always say that if science is no why, then engineering is no how. And basically, you always would like to go to the applications just for the fun of it. So thank you very much, Professor Weinland, on behalf of Indian National Academy of Engineering. We are actually the peer body of engineering in India, and we have about 800 plus fellows from India and about another 100 to 200 from across the world. And now that we know each other, we don't want to end the relationship only for one single occasion. We would like to borrow from your vast knowledge and experience in future. So on behalf of the entire Academy and on my personal behalf, please accept our earnest gratitude and appreciation for this wonderful talk, and also sharing your bits of your personal life. And I think what is outstanding here is that to continue to enjoy what we are passionate about. That's very crucial. So I'll also be failing in my duty if I don't acknowledge the role played by Dr. Sengupta and of NPL and Debatosh Guha of our Calcutta chapter of INAE for making this possible. And as I said, this is probably the first time that we are celebrating National Science Day under the aegis of Indian National Academy of Engineering, where a physics Nobel Laureate is delivering a distinguished lecture to celebrate the great discovery of C.V. Raman. We all indeed are very happy. I must also thank the INAE head office for creating the platform and all those participants, 100 plus consistently throughout, who have actually taken interest and stayed until the end. So with this, we come to the close of this session, and I thank you all, in particular, Professor Weinland, for this wonderful talk. Thank you and goodbye.